Hello, everyone. Thank you for joining us tonight. We have an amazing lineup of speakers today, and we're so happy that they were able to find time to join our meetup and to present at PyData Montreal. We're also happy that you, our listeners and attendees, are joined our meetup. We'd love to see you in person on a regular kind of meetup, but these days this is the best we get, and we feel that this is still a great opportunity to connect and learn from each other. I will let Alex give an introduction to what's going to be happening today, or rather tonight, depending where you are. And feel free to say hi in the YouTube chat, ask your questions, and just, socialize a little bit there. And with that, I'll pass it on to Alex.
All right. Welcome, everyone. So as mentioned, we have three speakers today. So we'll start off with Sylvain Gugger. He'll be talking, his presentation is on the topic of fine-tuning large language models without your own supercomputer. After that, we'll take a short 5-minute break so that everyone can grab their tea and so on. And then Julia Kreutzer will talk about learning to translate with JoeyNMT. Then we'll take another 5-minute break, and then Shubhanshu Mishra will talk about understanding digital social trace data with information extraction. And then we'll have a short kind of discussion, wrap up, and that's it. So we should be done in about 2.5 to 3 hours, depending on how many questions we get. Yeah. Sylvain, he is a research engineer at Hugging Face and one of the core maintainers of the Transformers library. Previously, he was a research scientist at Fast.ai, and he co-wrote Deep Learning for Coders with FastAI and PyTorch book with Jeremy Howard. And the main research focus of his research is to make deep learning more accessible by designing and improving techniques that allow models to train fast and on limited resources. Prior to this, he taught computer science and mathematics in France for 7 years. Sylvain is an alumnus of École Normale Supérieure in Paris, France, where he studied mathematics and has a master's degree in mathematics from University of Paris. So Sylvain, the floor is yours. You can share your presentation.
Yeah. Thanks. Can you all see my presentation?
Yes.
Yep.
Cool. So thanks for the introduction, Alex. Thanks for having me tonight. And I'm going to talk a little bit about how to fine-tune a large language model without your own supercomputer. So first, I'll go a little bit about what transfer learning is and what fine-tuning a language model means. I'll show a quick practical example, and then I'll show a few techniques on how you can still continue fine-tuning your language models when they don't necessarily normally fit on one device. And yeah, that's pretty much it. So thanks for the lengthy introduction. This slide is completely irrelevant. And I'm going to dive right into the subject. So transformers, you may have heard about them because they're all the rage in NLP right now. They were introduced in June 2017. Primarily for a translation task. So this wasn't a generic language model. This was a model that was trained, for instance, to translate from English to German. In June 2018, was released the first generic language model that was a transformer model by OpenAI, which was called GPT. And this model was pre-trained on a large amount of text data. And when fine-tuned on another task, like for instance, a text classification task or a question answering task, it kind of got state-of-the-art results without needing to start from scratch. The same approach was then replicated for lots of models. We have, like, for instance, 46, I think, architecture supported in the Transformers library right now. So in October 2018, the BERT model, then GPT-2, which was advertised and released a few months after, which has very impressive results, especially for text generation. T5 and BART in October 2019, very good for translation and summarization. And GPT-3, everyone kind of heard about that last year. And I also showed on this slide the DistilBERT model, not just because it was created by my current company, but because it's the only model that kind of breaks the trend. All of those models grew larger with time. DistilBERT is the only model that's smaller, and it's its only goal. It's a smaller version of BERT that's still as efficient and as good. And so pre-training those language models is something you generally don't want to do because it costs a lot of money. For instance, this is the estimated cost of pre-training GPT-3, and it's also not super friendly for the environment. If everyone was pre-training their own transformer model for every time they needed a model for a new task. So as you can see, with debugging architecture stacks, it takes the carbon footprint of approximately 5 cars. For the whole lifetime in the US. So that's why everyone uses transfer learning now in NLP, at least for most simple tasks. So transfer learning is the act of taking one of those large language models I showed before and fine-tune it on a specific task that's different from the one it was pre-trained on. And usually, it's very similar to what's usually done in computer vision, if you're familiar with that, where a model pre-trained on ImageNet is then fine-tuned on another image classification task or another kind of image task. The difference in NLP is that the pre-training can be done on just raw text without labels. It's a semi-supervised training, which means the labels are generated from the raw data. So that's why it's possible to pre-train like those very large models on basically the whole of internet without needing a human annotating every bit of the data. Whereas usually when you fine-tune your model, it's on a supervised task. That means a task where you have labels that have been created by humans. For instance, for a text classification task, someone will have said that this text has this label, this text has this other label, and so on. So those are examples on how those big language models are pre-trained. For instance, GPT is pre-trained using a next word objective, which is called a causal language modeling objective. So for instance, you give it it's supposed to guess name, my name is supposed to guess is, etc., etc. Whereas BERT is a tiny bit different in the sense that it looks at the whole sentence with some tokens in the middle masked, and it has to guess the value of the masked tokens. So in both cases, that objective doesn't need a human, like I said, to annotate the data. You can do that on the fly when you're pre-training a model and by taking any text you want. So for instance, BERT was pre-trained on a corpus that takes all of Wikipedia and a lot of unpublished books, and it's just masking randomly some words in the sentences to do the pre-training. And then your model is, the big models like BERT or GPT are shared online. You can download them and use them with the Transformers library. When you fine-tune them on your given task, you take everything except what's at the top. So usually your text has been encoded into integers with like, you split the words in your text into tokens. And then those tokens, you have a mapping, that's a vocabulary to convert them to integers because the model cannot understand raw strings, it can only understand integers. Those integers go through an embedding layer, and then the model with the transformer models with all its layer. And at the end, there is a decoder that's going to convert the last hidden states into something where you can get back hints again for the pre-training. So when you're fine-tuning on a new task, you remove that decoder head and replace it by a head that's suitable for your own task. So if you have a text classification task, it's something that's going to output as many labels as you need. If you were doing something like for question answering, it's going to be a different head. For summarization, it's going to be a different head again, etc., etc. And so that's the theory around fine-tuning. If there is any question at this stage, I'm glad to take them. Otherwise, I'll show a practical example on how to do that. Tick, tick, tick. I'm gonna guess there is no question. I can't see anything and I can't hear anything. Can you still see my screen? Tick, tick, tick.
Yes, we can see your screen and we can
Sorry,
hear you.
Since I couldn't hear anything, I was kind of worrying that I have been disconnected somewhere. Sorry. So
Could you zoom in a little bit, because this may be a little bit too small.
No problem at all. Thanks for making me feel less alone. So we're going to go through a quick example on how to do this fine-tuning on a text classification task, and if I have time, a summarization task next. Using the transformers library and the Hugging Face datasets library, which you may or may not know about, but it's a library that, so the transformers library is a library that allows you to quickly download and use the transformer models, and the datasets library does the same, but for common datasets in NLP. So let's fine-tune a model on a text classification task. So here I've chosen to fine-tune a model called T-Stilbert Bayesian case. So at Hugging Face, we have a model hub, which is a website where you can get information on all the models we provide. So if I click on the link of the checkpoint, I get a nice page that tells me what this T-Stilbert model is. There is a small widget. So it's like BERT. It was pre-trained by having to guess the value of some mask token. And I get a nice widget that showcase those abilities. So for instance, here Paris is the mask of France, and it correctly guessed capital with a probability of 98.2%, and then some other words with smaller probabilities. So I can try actually the performance of my model on the given task directly online. And then I get some model descriptions, the intended use and limitations, how to use it into transformer with small examples, the limitation and bias. So for instance, this T-Stilbert model, even if it was pre-trained on Wikipedia on a corpus of unpublished books, has still some race bias and gender bias in it, because if you ask it to guess a word in the white man worked as a mask, it's going to guess things like carpenter or blacksmith, but for a woman, it's going to guess prostitute or housekeeper. So all of this is on this page, and all the model works in general. So if you can navigate the model hub, pick another checkpoint if you would like to fine-tune another model on this task, and all the book is going to work all the same. We use the datasets library to load the datasets. So for instance, here I've taken the MRPC dataset, which is a part of the GLUE benchmark. It's a small dataset, that's why I picked it, that contains pairs of sentences, and you have to say if the sentences are paraphrase of one another or not. So I can load it super easily with the command load dataset. I can load the metric associated with the dataset super easily with the command load metric. It returns load dataset a raw datasets object, which is a dictionary that has the training split, the validation split, and the test split. And then each time some dataset associated with it. And I can see a sentence 1 key, sentence 2 key, and a label. I can access one element of the training dataset and look at it. And I wrote a quick function to just show some elements in a small table. So we can see the labels are equivalent or not equivalent. And then for each of those examples, the actual two sentences. The metric that was loaded is an instance of a dataset.metric object. It's very easy to use. It's a bit like the scikit-learn metric. You just have to pass it predictions and labels, and it's going to output you. So here, the accuracy and the F1 score. So it's on some random data, so it's not very good, obviously. The accuracy and the F1 score are usually the results of models fine-tuned and MRPC are evaluated on the GLUE benchmark. And so to pre-process the data, the transformers library provides a class called AutoTokenizer. The AutoTokenizer, it's because it's going to work for every kind of model. So it's not a BERT tokenizer or T-Stilbert tokenizer or, I don't know, T5 tokenizer. It's going to detect from the model checkpoint I gave it what kind of model is associated with it, so what kind of tokenizer is associated with it, because we have to do, since we are using a pre-trained model, we have to do the pre-processing exactly as it was done for the pre-trained model. So here I load it with the method .fromPretrain, which is going to download the vocabulary and cache it on my hard drive. so the vocabulary associated with the model. I can then pass to the tokenizer one sentence or a pair of sentences, since here our problem is about pairs of sentences. I've given an example with a pair of sentence. So it splits, it's going to concatenate those two sentences, split them into tokens, and then map each one of those tokens with an integers, like we saw, because as I said before, the model is going to take those integers and inputs and not the raw text. So it does all the preprocessing, and if you're very familiar with Robertworks, it's also adding as a special token like CLS and SEP. If you're not familiar with those, don't worry about it. It's not super important because the tokenizer is doing it for you. So you can do it for one pair, you can do it for two pairs of sentences. You just have to pass the list of first sentences and then the list of second sentences, and it returns, in this case, list of lists. The second element, the attention mask that you can see here, is going to be useful a little bit after, because we can't really see it there. But for instance, in this example, the two pairs of sentences don't have the same length when they are preprocessed. And so I won't be able to create a tensor with the two of them right away. I'll need to apply some padding. So that means adding a fake token at the end of the shortest sentence. And then the attention mask is going to contain 0 when there is that padding. So that's why it's going to tell the model, don't pay attention to that, it's not important. And then, so to preprocess my dataset, I can create a small helper function like this, which just applies the tokenizer to the first instance named sentence1 and the second instance named sentence2. The truncations equal true arguments is there because my model, the distilled model, has a maximum length of input it can receive. So if I give it an input that's longer than, I don't know, I think it's 512, it's going to crash. So to avoid that, I'm going to truncate. If I have a very, very long pair of sentence, I'm going to truncate it to that maximum length. And then I can preprocess a split of my datasets, or even all the datasets at once with the map method. And once those datasets are preprocessed, I just have to load my model. So here it's a sequence classification task. So I'm going to use the class called AutoModel for sequence classification. And like my auto-tokenizer, it's a generic class that's going to detect which type of model I have from the checkpoint, download it, cache it on my hard drive. And then it's also going to do all the stuff we saw in the last slides, which is removing the head and replacing it with a head suitable for sequence classification. That's why I have to say it, I want 2 labels. And that's also why I'm receiving this big warning in red, which is not, it doesn't mean I'm doing anything wrong. It just means that we have removed some of the weights and replaced them by some randomly initialized weights. And that's why it ends with, you should probably train this model. So the warning just tell me, don't use that model on any sentence and expect it to be good. You have to train it to fine tune it on your task before it's going to give any good results. And then to make the fine-tuning of the model super easy, the transformers library provide 2 classes, the main class being trainer, which is going to train my model, and training arguments is where I can put all the hyperparameters for my training. So I'm picking a batch size of 32. I'm going to evaluate my model every epoch. I use this learning rate. I'm going to train for 5 epochs. I'm putting a bit of weight decay. And since my dataset is very small, it's very likely that I'm going to overfit pretty soon. So I just add those 2 options to keep track of the best model on the accuracy metric and load it at the very end, so that I have the best model at the end of my training. And yeah, just before passing everything to trainer, I need to define a compute metrics function to tell it how to compute my metrics from the predictions. So it's all done by the metric function we saw before. I just have to take the argmax of my predictions, because the predictions I'm going to have is going to be a tensor of the size of my batch by the number of labels. So I take I'm going to pick the label that got the maximum score with the argmax before passing everything to metric.compute. And I feed everything to my trainer, the model, the training arguments, the training datasets, the evaluation dataset, the tokenizer, and this compute metrics function. And it's going to be able to train my model. It's also, like I said before, my samples are not all the same length, so I'm going to need to apply padding. And I didn't do that in the preprocessing, because if I did that in the preprocessing, I would have had to pad to the very maximum length of my dataset, which is not super efficient. The trainer is actually going to pad for every batch to the longest element of the batch. So it's going to be a little bit more efficient, since if I have a batch with small pair of sentences, I won't need that much padding. And this is all done automatically. That's why the trainer needs the tokenizer here. It's going to take the padding index of the associated with the tokenizer here, and the padding method associated to the tokenizer here. And I can train it, and I have some scores that come relatively quickly. I think it takes 1 minute on my hard drive to fine tune on this dataset, because it's a very small dataset. So it's a very good dataset to play around and experiment. And I can evaluate at the end, and I get the same results as my best model, which was in this case the model at hand. But sometimes here we start overfitting, and the metrics are not increasing anymore. So this is exactly how you can fine-tune a pre-trained model from using the transformers library. Can take questions at this stage, if there are any, before I go to the summarization example.
Right, Sylvain. So I actually have quite a few questions.
Oh.
Right. So at the very beginning, where you had sort of a diagram, sort of the body of the model and your custom head of the model, can you elaborate a bit more on how do people who actually want to have this custom head for the model, how do they go about creating this structure for it? How complex should it be? How many layers should the head have, and what it depends on?
So usually it's the whole complexity is usually inside the big transformer model here, and usually those classification head don't need to be very deep. 1 or 2 layers is usually enough. So for instance, in the example I was doing just after, the auto model for sequence classification model has 2 layers on top of the rest of the model.
Okay, and from your experience, does it make any difference? Let's say if someone works with highly specific text data set, let's say from like some scientific field, like maybe medical field, versus someone who's classifying Twitter data, would the structure of the head change depending on the data set?
That's a good question, and I don't know. So my answer would be to try a few different things and see how it changes.
Okay. Yeah, and another question I had sort of related to this one is, should someone try, like if they have a text classification task, should they try pre-trained embeddings first without even trying to fine-tune their head? Or should they just go straight ahead and kind of fine-tune for their own specific task?
Yes, definitely. I mean, especially if it's on not a lot of data, fine-tuning on the specific task is not going to take a long time. Like in the example that you saw, it takes 1 or 2 minutes for a small data set. So you're going to get the best results, and it's not very expensive to do so. So I would always say to fine-tune.
Okay. Also, at some point, you were discussing, this is maybe a more nuanced thing, that if you have 2 sentences of different length, you pad them at the end. Why at the end, and why not pad from the beginning?
It depends on the model, actually. I said at the end because it was the case for the specific model I was using. It was pre-trained that way, so that's what it's expecting. But in general, you should always follow the same strategy as when the model was pre-trained. That's why the tokenizer it has a pad method, and it knows exactly how to pad your text, and you should. If you use the transformers library, you should use that to pad your text directly. And if you don't use the transformers library, be sure to check how the model was pre-trained to do the same thing.
Okay. And I'm guessing some people in our audience might have used, like if they work in NLP, they might have used Spacy. Let's say they have a work project that relies on Spacy. So how does like Transformers library kind of fit, like if they want to try it? Is there a replacement for Spacy? Is that like, does it have complementary functionality?
It's different functionality as far as I know. Spacy is more going to help you for I mean, it's mostly linked around tokenization and then getting the named entities or the structure of your text, whereas Transformers is really all about the Transformers models and how to fine-tune them to your specific task.
Okay, got it. And final question, and I'll let you continue. So from your kind of previous experience in working at Fast.ai, what ideas have you kind of implemented in the Transformers library? What ideas kind of proved to, to work very well with Transformers?
So it's mostly about transfer learning, which is the same kind of thing we always advertise in the course at Fast.ai, because it's so powerful. You're using that pre-trained model that's been trained by a very big company, and in 1 or 2 minutes you can get amazing results and not a lot of data that you maybe manually annotated. So that's the main idea, I guess. But it was already there before I arrived at Hugging Face, but that's a continuation.
Okay, perfect. Thank you.
There have been also a couple of questions in the chat, and one of them, can you do model parallel training for very large parameter models in PyTorch?
So we'll get to model parallelism a bit later.
Okay, great. And then one more, which should also be quick. Why the padding can be shorter if sentences are shorter in a batch? Okay,
so in your data set, in the world data set, you can have like pairs of sentences going from, 25 tokens to 150 tokens. But when you are in your batch, you only have, the batch has of 32 in my example. So you only have 32 elements of those data sets. So if you're lucky, you have 32 short elements together. So you won't apply padding up to 150, the maximum of your data set, if you do the padding at the moment you create your batch, which is called often dynamic padding, sorry. And whereas if you were to apply padding on your dataset, you have to do it at the very maximum length of your dataset, so it's not as efficient.
All right, thank you. We can get back to the questions at the next step.
Yeah. I'm just going to go very quickly over the summarization example because I want to keep time for the rest of the talk. And also, it's very, very similar to the text classification example. You still get your model checkpoint. You still get a model card for your checkpoint. It's called T5. This one, so T5 can do translation and summarization. The small widget you have on the website is just about translation, English to German. And then you load the dataset in the exact same way. So here I'm using the XM dataset, which is for extreme summary. It's a dataset of BBC articles that have been summarized in 1 sentence. And so it's the same way. You have a raw datasets object that contains, that's a dictionary split to actual datasets. You can access the elements like this. I have the same function that show a few random elements. And here the columns are document and summary. And it's tokenized almost exactly the same way. You get an auto tokenizer that you have to download the vocabulary that's associated to the model. And here it's not pairs of sentences, it's an input sentence and a target sentence. So I'm using the tokenizer with just 1 sentence. And for my target, I'm still using the tokenizer with 1 sentence or a list of sentences, but I have to put it inside a context manager to tell it you are tokenizing targets. So it's super useful mostly for translation, because when you switch languages, your tokenizer has to do something different usually. And so my preprocess function is a little bit different from before, because my task is a little bit different, but not that much. So I'm passing my documents to the tokenizer and my summary to the tokenizer. And I've set a maximum length that's different from the input in the targets, because it's a summarization task. So my summaries should be short. So my inputs, I truncate them at 124 characters, tokens. and my targets, I truncate them at 128 tokens. And the same way, I can apply my preprocess function on a slice of my dataset. I can tokenize everything together with my preprocess function with the map method. And the fine-tuning looks very, very similar. It's just the class of the model that's different. It's a model for sequence to sequence because it's a sequence-to-sequence task. I have to use a smaller batch size, even if I used a very small checkpoint. It's called T5 small, and it's not the T5 11 billion parameters. But still, I have to use a smaller batch size than in my classification task with T-Stilbert. And I also used FP16, which we're going to talk about later in the talk, to actually get a little bit of memory free and also speed up my training. The only difference is in the compute metrics function that's a little bit more complex because my metric here is taking decoded text. So I have to decode the text before passing them to it and cleaning them a little bit. And then the other difference is I can't use the default to create my batch. I have to use a specific data collector. So the data collector in PyTorch, it's the thing that takes a sample of your data set and creates a batch from it. So it's not the default one because I have to pad my input, but I also have to pad my targets since my targets don't necessarily all have the same size either. Before, in the text classification task, they were all just labels. So it was easy to create a batch from that. Here, my summaries could have different length. But it's the same philosophy. It's all going to be padded at the moment I create the batch, which is a little bit more efficient. And then I pass my training arguments, my dataset, my training dataset, my validation dataset, my specific data collector, the tokenizer, and the compute matrix to the trainer, and I can train it. Here the dataset is quite large, so it's taking 1 hour and a half on my machine, but you get the idea. The API in general is very similar to what we had in the previous task. And let me go back to my slides. Like I said in the slides, you have like 2 links with more examples, either as scripts or as notebooks. Then you can click on those links to access them. Present again from the beginning. And so the problem that we are now going to talk about is that the transformers models are larger and larger models. And so in my summarization example, for instance, I took the smallest of the T5 models, and you can see the big one is here with 11 billion parameters. So from the first GPT model to now, so that was from Microsoft, and GPT-3 is of the chart around here, all the models have increased a lot in size. And the problem is that when you try to fine-tune it following the same steps I have shown you in my notebook, you're going to get this error. Which means that there is no memory left on your GPU. It's going to be different if you train on GPU, but you still have device space that's pretty limited. And to train those very large models, we'll need to be smart and we'll need to apply some techniques. So usually when you're out of memory, the first advice everyone gives you is to reduce the batch size, because it's going to take your activations and your inputs, and all the hidden states inside your models are going to take less space. But that only works if you can still get decent results with batch size of, say, you can go maybe to 8, and under 8, you're going to get some less good results, just because for gradient diff, for the usual algorithm of gradient descent to work, you need to have batches of a certain size. So that's where all the other techniques can come and help. We're going to look at gradient accumulation, gradient checkpointing, which have been around for a while, and then some pretty recent developments. And when I say pretty recent, some of the things I'm talking about have been released on Monday by, for instance, Fairscale, which is a library developed by Facebook A Research. So it's very, very recent, which all come from a paper called Zero, developed by a team at Microsoft. And I'm also going to talk a little bit about model parallelism and pipeline parallelism. What's pretty exciting is that the first 3 techniques, and even so zero offload, can all be applied if you have just 1 GPU. It's only the last 3 techniques that need several GPU. So even with 1 GPU, there's a lot of stuff you can do, and you can still not maybe fine-tune the 11 billion models of T5. If your GPU is a very big one, it's possible, but you can still fit pretty large model. We'll see a little bit about that very soon. And so before I delve into those techniques, we'll just need to know what actually takes place on your GPU or your TPU when you're training. So let's just look a little bit about what's happening when you're doing training. So schematically, it's looking like this. You have a model, you feed it input data, and there is a forward pass, which is your input data going through the model. It's compared to the targets, and you get a loss. And with this loss, you can do the backward pass, which is computing the gradients of the loss with respect to every model parameter. And once you have those gradients, you can do a little step in the opposite direction, which is called the optimizer step. And when we look at all those steps, what's happening and what's on the GPU and what takes place on the GPU. So for the forward pass, it's first your model. Your model takes place on the GPU and needs to be there. And then all the intermediate activations, all the hidden states are stored when you do the forward pass because they're going to be needed for the computation of the gradient. So they are stored, sadly, on your GPU and takes place there. Then in the backward pass, the gradients of the intermediate activations are also stored on the GPU, though it's going to free a little bit of space because you won't need all your intermediate. I mean, once you've used your intermediate activations, they're not needed anymore, so you can forget them. Then the gradients take place on the GPU. And if you're using an optimizer like Adam, it's going to take the optimizer itself as a state that takes some space on the GPU. So for instance, Adam, you're keeping track of the average of your gradients or the average of the squares of the gradients. And those two things take some space on your GPU. So if we group those, there are two categories of things taking space on the GPU, the activations and model and everything related. The activations have a size that depends on your batch size, on your maximum sequence length, because usually it's all tensors of dimensions, batch size, by sequence length, by hidden state of your model. On the other hand, the model and the gradients and the optimizer states, those are all directly proportional to model size, because all those things, it's you have one gradient per parameter of your model, and your optimizer state is exactly the same size as your gradients or twice the size of the gradients, depending on how many things you store. So in the case of Distilbert and the text classification example we saw, the Distilbert model by itself takes 255 megabytes of memory. So 1 gigabyte of memory was used by the model gradients and optimizer states, and the rest of the memory consumed. So here 3.6 gigabytes was taken by the activations. So usually when you're fine-tuning, it's the activations that takes a lot of space on your device. So reducing the batch size is a smart thing to do because it's going to reduce the size of the thing in green. And if you have to get to a very, very small batch size and don't want your training to be unstable, you can use the first technique called gradient accumulation, which is going to be basically emulating a training at a higher batch size without taking the space in memory. So for instance, here, I'm training at batch size 4 in my data loader with 8 steps of gradient accumulation, and it's exactly the same thing as if I was training at batch size 32. So how do I do that? So my data loader has a batch size of 4. I do everything I'm used to do in PyTorch. So I get my batch, I pass it to the model, I get my loss. I do loss backward, but I don't do the step for every batch. I wait a few batches. I wait exactly gradient accumulation batch to do the step. That's because in PyTorch, the gradients are added each time you do a loss backward. So they are accumulated. That's why here you have the line loss must be divided by the gradient accumulation steps, because otherwise it's not going to be a true mean over everything you've seen. And you only do the steps every gradient accumulation steps. And all of that is very easy to do in PyTorch, like I said, and it's going to be a training exactly as if you were training at batch size 32. So with this, you can actually reduce your memory footprint to go to batch size 1, the smallest possible. And if you do just a gradient accumulation of whatever you want, like your batch size to be. And for big models, it can be enough, and for you to be able to fit them on your GPU. If it's not enough, you can add another thing called gradient checkpointing. So as I said before, you have to store all the intermediate activations when you do the forward pass because they are used to compute your gradients. The problem is that it takes space on the memory. So here we have a diagram of what usually happens when you do the forward pass. Here you have your output of the model, and then with that you compute the loss. And you have to store every intermediate activations for the gradient, for the backward pass when you compute the gradients. And only when you have used them to compute the gradients, you can free the memory that was used by it. But basically, you will need all that thing in purple to be accessible in memory to be able to fully do one forward path and one backward path. When using gradient checkpointing, you actually store only, let's say, every other intermediate activation. That way, you will use half the space. But when it's time to compute the gradients, you can't compute them directly. You have to use your checkpoint. So if I'm going to wait for the animation to come back here again, you have to use, when I'm here and computing that gradient, first, if this activation is recomputed from this checkpoint, and then I can compute that gradient. So I'm spending a little bit more time during the backward pass because I have to recompute some of the activations I didn't store in the exchange of freeing some memory. So with this, you're going to have a longer training time, but if your model wasn't able to fit in memory, you're going to be able to fit your model in memory. You can take questions at this stage before diving into the next technique, if there are any. Otherwise, I'll just continue.
Yeah, there are a few questions from the audience that we can ask. So first question from Leo. So in those two examples, but there was a few slides earlier, the fine-tuning is done on the whole model. When should one consider to lock model parameters and only fine-tune the head?
So that's what's usually done in computer vision. For transformer models, for some reason, it doesn't work as well. So usually, in most cases, you fine-tune directly the whole of it. It maybe needs to be studied further, but yeah, I haven't seen successful examples yet where you freeze just your whole model and just fine-tune the head and still get good results.
Okay. And another question from Ben. There was during the time when you were doing the live coding, like presenting your Jupyter notebook. So what's the difference between a regular tokenizer and a tokenizer in as_target_tokenizer context?
So the difference is that if you have a translation model, the tokenizer is going to be multilingual. For instance, it can tokenize English, Chinese, German, Spanish, etc. But maybe it needs to be different when it's tokenizing in English versus tokenizing in Spanish. So when you set it in the target mode, it's going to have all the specific states it needs to tokenize your target. So if it has a different language, it's going to have the specific state it needs for that.
Okay. And one more from the audience. Salman is asking, if there are multiple different classification tasks, is there a way to train the BERT model with different heads in a multitask fashion?
Yeah, you can definitely have a multitask model for different classification tasks. You just have to write the code for your custom head for that.
Okay.
And so if that was all, let's dive into the next technique to save memory. So it's actually a technique to save memory and get more speed, contrary to gradient checkpointing, which is training in FP16. So if you don't know a lot about floating precision types and how floats are stored in your computer, don't worry too much about it, but we need to dive a little bit into that. So your computer does not store floats as numbers with an infinite number of digits because it doesn't have an infinite space on its disk. So it's using a certain amount of memory to store each float, usually 32 bits, which is 4 bytes, and for the usual floating point precision. So one thing we could think of when we want to save memory is to use half the space to store all those floats number in a floating precision format, which is called FP16. So that's an idea. The problem is that since you're not storing the number with like the infinite number of digits after before or after the comma, the dot, sorry. The problem is that your small numbers become 0 at some point. For instance, in the usual floating point precision, when you get below 1 e and neg 40, you start to become just 0 instead of become a very small number. And if you're in FP16 precision, small numbers are 0 much more quicker. And the same for large number. Large number become infinity much quicker. And the problem is that when you're training, your gradients are usually very, very small. So if you're training in FP16, your gradients will all be 0, and you won't be able to do any step. And some of the activations are very, very large when you're training your model. So in the same way, when you're training in FP16, you take the risk of having your activation becoming infinity much more quickly. So that's why training in FP16 without doing anything special just doesn't work. But thankfully for us, some engineers at NVIDIA developed an algorithm called mixed precision training, which allows you to train with some steps in floating point 16 and some steps in floating point 32. To be more precise, it's the optimizer step that absolutely needs to be in full precision, so FP32. And then everything else can be done in half precision if you do it properly. So the forward pass and all your activations can be stored in FP16. Then the loss has to be computed in FP32, but the loss is just one number, so we don't really care about it in terms of memory, I mean. And then before doing the backward pass, the loss is multiplied by a large number, just because that way all the gradients are going to be larger. And as I said before, in FP16, numbers become 0 much more quicker. So if you multiply the loss by a large number, let's say 124, that way all the gradients are theoretically much larger, and in your backward pass in FP16, they don't become 0. And just before doing the optimizer step, you convert your gradients from FP16 back to FP32, and you divide them by that large number, 124, you use to scale the loss, so that they are the actual real value of the gradients. But that way, it's a very smart trick to not have them become 0 during this step. And you can do this step in FP16. So that's kind of cool. And it uses less memory, but we'll say about that. But mostly it's been designed because it's much more faster as well. Because operation in FP16 on GPU that have the capabilities can be like 4 to 8 times faster than operations in full precision. The problem is that for the impact in memory, if we look at everything we had stored on the GPU, our activations take half the size, but the models needs to be stored in the 2 format, because we do the forward pass in FP16, but the step in FP32. So we need 1 copy in half precision for the forward pass and 1 copy in full precision for the optimizer step. So while the activations take half the space, the model is going to take 1.5 the space. The rest is the same. But in practice, if we look at it, so this is a slide with different batch size, we see that, yeah, we don't save much memory with FP16 for batch size 8, and for batch size 1, which is missing on my table, it has actually a negative impact on memory. It takes more memory to train FP16 than training without it, because of what I just said, activation half the size, but model plus 0.5 the size. So why am I talking about that? That's because on top of mixed precision technique, the Zero paper I was talking about before has added an innovation that's very, very cool. And the idea is you have to store your model in FP32, why not? But why not store it on the CPU instead of storing it on the GPU? This way, you only have the copy of the model in half precision that sits on the GPU, and you will save a lot of memory. And if you have your model in FP32 on the CPU, that means you must do the optimizer step on the CPU. But the optimizer step, it doesn't require a lot of compute. It's just saying parameters equal parameters minus learning rate multiplied by gradient. It's something very easy to do. It's not like the large model. So that can be done on the CPU. And if you do that on CPU, that means you can store the gradients and the optimizer states on the CPU as well. This way, you save tons of memory on your GPU, because you only have on your GPU the activation in half precision and the model in half precision. And you do the forward pass on the GPU, the loss on GPU, and the backward pass on the GPU. It's just that during the backward pass, each time you compute the gradients, you store it on the CPU instead of storing it on the GPU. And with this, you can actually fine-tune the T5 3B, so 3 billion parameters models on a single RTX 3090 card that has 24 gigabytes of memory. And if you go for the A100 card that has 40 gigabytes of memory, you can fine-tune the very large T5 models of 11 billion parameter, a feature that's normally accessible only if you have at least 8 GPUs to parallelize your model. So that's really, really cool. And then the second half of the Zero paper was introducing zero data parallelism. So for this part, and until the end of my talk, you need several GPUs. Everything up until now only needed one GPU, but for the rest, you're going to need several. So the idea behind zero data parallelism is that if you're doing a distributed training, you have on all GPU the model, a copy of the model, a copy of all the gradients, and a copy of all the optimizer states. And that doesn't seem super efficient because it's the same thing copied on all your GPUs or TPUs. So the idea behind zero data parallelism is to split your either optimizer states or gradients between all your available GPUs so that you can save memory. So those three lines in the diagram are called 0DP stage 1, 0DP stage 2, and 0DP stage 3. In stage 1, we only shard the optimizer states. In stage 2, we shard the optimizer states and the gradients. And in stage 3, we shard the layers of the weights of the model, the gradients, and the optimizer states. And stage 3 is a thing that was actually released just on last Monday. It was only theoretical up until a few days ago, but it's been released by Fairskill and should be released pretty soon by DeepSpeed on Microsoft side hopefully in a couple of weeks/months. So this is super exciting. If you have like 2 to 8 GPUs, you will be able to fit super large models by using these techniques. A small precision on here, when you split the models, you're splitting the models horizontally, sorry. That means that one layer is split across all GPUs. Another technique where you can save memory and use all your GPUs is called vertical model parallelism. In this technique, you have, let's say, if we say for simplification that our model has 4 layers, you put the first layer on GPU 1, the second layer on GPT 2, etc., to your GPU 4. And then when you have input data, you give it to GPU 1. And then when GPU 1 is finished, GPU 2 is going to take the output and compute the output of the second layer. When GPU 2 is finished, it's going to give it to GPU 3 and compute the output, etc., etc. So this saves a lot of memory. The inconvenience is that it's super inefficient. As you can see, all the gray thing is when the GPUs are waiting because it's not their turn, and you have got a lot of that. So on the one hand, it allows you to train a larger model because you basically have 1/4 of the model on each GPU. But on the other hand, not super efficient. And if you are doing that, you're probably at the stage where your batch size is 1, because otherwise you would have other techniques to reduce the memory used on your GPU. So you're not actually doing one step every batch, because with batch size 1, you are probably going to have a gradient accumulation step of 8 or 16 or 32 to have an actual batch size of 16 or 32. So you can be smarter, which is called pipeline parallelism, which is just scheduling, like once GPU 1 is done with the first example, why not give it the second example? Because it's going to have to wait a lot of time before the first example is completely done with the model, and needs to go back to the model again for the backward pass. So pipeline parallelism is the act of scheduling your data so that each GPU can kind of work in parallel with the others. And if you do it smartly, you can arrive at a state where every GPU is working either for the forward or the backward pass, and you only need to synchronize them when you have done like, I don't know, 16 or 32 of those things. So you're losing a bit of time here, you're going to lose a bit of time at the end, do your optimizer update, and then start a new cycle like this. But this way, it's way more efficient than model parallelism, and you still have on each GPU 1/4 of the model. So you still have the same memory saving, but you're going to train way faster. So that's all for the overview of the technique I wanted to show you today. Like I said, it's been an area of very active development. I had to redo that slide 3 times in a week, actually, because like the library is also FairScale is a library developed by Facebook AI Research. DeepSpeed is a library developed by Microsoft, and SageMaker is a library. There are some tools developed for AWS, SageMaker, by the AWS team. So I've put a summary of gradient accumulation and gradient checkpointing have been around for like a couple of years. They are all implemented in basic PyTorch, so you have them everywhere. Same for mixed precision, which has been added to main PyTorch in the 1.5 or 1.6 release. And then for the zero offload and zero data parallelism, it was originally coming from DeepSpeed, but only with zero stage 2. And FairScale just added it, like I said, last Monday with the stage 3. Which is splitting not only the optimizer states and the gradients, but also the model parameters. And then model parallelism and pipeline parallelisms are available on FairScale, DeepSpeed, and SageMaker with different kinds of implementations. And we try to keep up to date with all of those in our main Hugging Face trainer, so that you are able to use all of those tricks to accelerate your training and to save memory. And that's all I wanted to talk about today. I put a lot of resources on the slides, so I've shared the link to my slides, so you can click on those links at the end if you want to learn more about all those core features. And if I have still a bit of time and there is questions, I'm happy to take them.
Thank you so much. It was a very interesting presentation. There are a lot of techniques to use to reduce the memory footprint. Thank you. It was very interesting. We have a couple of questions from the chat. One is, what's the impact on training speed with zero offload?
So the libraries that develop it have been trying to minimize the cost in terms of efficiency. So this is only for GPU. It doesn't exist for TPU as far as I know. And it doesn't cost that much speed actually to offload the weights on the CPU. And also with the mix, since it's coupled with mixed precision training, which as I said, like the operations in FP16s are way faster, you actually are going faster than a regular training on the same device.
Mm-hmm. Another question that we had was, by using the CPU, do you not slow down the training as you have to communicate between the CPU and GPU?
I mean, usually the communication is fast enough that it doesn't slow down the training.
Mm-hmm.
And like I said, it's not done directly in PyTorch. Like it was a specialized library that have code in C that is doing that behind the scene. It's not the actual user doing that in his Jupyter notebook. So that's also why it's efficient and fast.
Yeah, typically when people who are experts on optimizing things will do it better than most of the other folks working in Jupyter notebooks. Not always the case, but for the most part. So another question was, how much extra time does gradient checkpointing add?
So usually it's like your backward pass will be like twice as slow if you are forgetting every other activation. So if you activate it to only store half the intermediate activations, you can expect the backward pass to be twice as slow.
Mm-hmm.
And if you try to forget, like if you only store 1/3, it's going to be 3 times slower, etc., etc.
I think we have time for one more question, and then we're going to continue with our next speaker.
Mm-hmm.
So the one more question is NVLink required for GPU parallelism to really benefit from it?
I haven't tested without NVLink, but I would say, yeah, that's probably necessary. Otherwise, the communication between the GPUs is not going to be fast enough.
Okay, there's one more. Somebody is saying that it's a superb talk, and I couldn't agree more. It was an excellent talk. And
Nice.
You mentioned that you updated your slides 3 times in a week. And how do you keep up to date with the progress of these libraries?
I mean, it's a lot of work. I mean, I've worked a lot on that this week, especially. Fortunately, they don't. I mean, it's not every week like this. Fortunately, there are weeks that are developing on their side and not releasing stuff. So it's not been a super busy month up until this week. But yeah, it's a subject where fortunately there's a lot of active development, which is super cool because those models, those language models in NLP are not going to become slower. They are just all of them are going to become bigger. So if we still want common folks to be able to use them and to democratize transfer learning, all those techniques are super useful for that. So I'm really passionate about them. That's also how I keep up with them is that I don't mind sleeping an hour less just to read one more paper about it.
Yeah, but kudos to you. It does take time to keep up with things.
Yeah.
Thank you again. I would like to introduce our next presenter. I'll just add Julia to the stream. Hi. So this is Julie. Julie Kreutzer is a research scientist at Google Montreal, where she works on improving machine translation. She holds a PhD in computational linguistics from Heidelberg University in Germany, and is also part of grassroots community Masahane, I hope I pronounced it correctly, which aims to build NLP technologies for all Africa's languages. She deeply cares about open source accessibility and creativity in NLP research. I hope I pronounced that correctly.
Yeah, almost.
Almost. So Yude is going to be talking about learning to translate with JoeyNMT. Could you share the slides, please?
Yeah. Sorry, it always takes some time to find the right
No worries.
thing to share. Can you see the slides?
Yes, it's great. We can see the slides.
Okay,
we
perfect.
can see you. We can hear you. And so with that, take it away.
Thanks a lot for having me. And I would be I'm super excited to be here, but I would also be super excited to meet you all. So as soon as we're going back to real
For sure.
real life meetings, I'll be there. I moved to Montreal 1 year ago, so I'm still pretty fresh. Yeah, so this is work that I did before joining Google. This was done during my PhD. I built this framework JoeyNMT with a friend. And yeah, I'm going to talk a little bit about translation because I work on translation now in my research as well. And it will be, I'll give you a little introduction. Just shortly. So first, we'll talk a little bit about neural machine translation as a machine learning task. Some important notions there are, some of them are shared with other tasks, NLP tasks. Some of them are a little bit more specific. So we'll talk about the transformer model again, that you should probably already know, and the role of data. And then in the second part, I will talk specifically about JoeyNMT, the toolkit, the features. We'll have a demo. And some use cases where it has been used that are actually really cool. So throughout the talk, I encourage you to write questions in the YouTube chat, and I'll catch up on them in the end. I'm assuming some basic machine learning knowledge, familiarity with neural networks, but if you can't follow up with the technical details, I'll try to make the intuition really clear. And yeah, you can follow up with questions later on. All right, so before we get into the neural machine translation part, if you want to follow along for the demo and build your own machine translation model, you can open the JoeyNMT demo notebook on Colab, create a copy, and start running it on a GPU. So you just have to click run all. And then you can come back here and we'll look at it, what's happening there later. But it's basically it's going to train a machine translation model over the next few hours, if you wish. But I have one running right now, and we'll look into it, what's happening there. And I think the link will be posted in the chat. But you can also, if you go to GitHub, search for JoeyNMT, and there's one notebook in the main directory, you'll find that. So let's talk a little bit about the problem of translation. So here we have an example for translating from French to English. So here it's a pretty simple sentence. I try to align the words that belong to each other so that are translations of each other. So some parts of it are very easy. So poutine and poutine is pretty fairly straightforward. And it's here translating like a question mark. The question mark is also pretty straightforward. And then A, you have to decide whether you translate it to une or un. And that's already a little bit more complex because that kind of feature is not realized in English, but you would have to realize you have to pick a gender in French. And then it gets really complicated in terms of like matching between those two languages, because in English we just say what, and then in French you have to use that whole phrase. That's even complicated for human learners. So this is a little bit where it gets challenging for machines as well. So the problem is that we'll give our machine learning model this kind of input sequence, and it has to generate this output sequence. And there's a few characteristics that make it harder or hard. So one of them is that this input sequence can be arbitrarily long. It could be a whole document. It could be a very short sentence of just 2 words. In principle, it can be anything. It's language. It's doesn't necessarily have to have an end. So our models have to be able to deal with arbitrary length input. In real life, in the models that we build, we usually split them at sentence ends. So we try to find out, okay, a question mark probably means the sentence ends here, so we translate sentence by sentence. There are also now a lot of approaches to translate on a document level or to incorporate some kind of external content or to increase the context size for translation. But the technical solution that we're using for modeling arbitrary length is also to rely on recurrent mechanisms for generation and attention mechanisms that can span that don't have a fixed input length. And then more on the linguistic side, there's a lot of structural dependencies, both in the source sentence, so what is a poutine, and also on the target sentence, because, for example, you need to pick, as I said, you need to pick the right article for the noun here, and then dependent on the words you choose in the source, you might have to reorder them in the order might not be the same in the target sentence. So your model needs to be able to reorder information dependent on the language and the information that is present. So for that, the solution that the transformer, for example, provides is that it has a tension mechanism between all the words in the output and also in the input, and you can have a connection between them. And so you have the intra-attention mechanism and the cross-attention mechanism that connects output positions with all input positions. So you need to have a way to let information flow to be able to learn these structural dependencies or connections. And then one particular problem that is nowadays, I would say, almost solved, at least there's much better solutions than like 4 years ago, 5 years ago, which is the problem of unseen words. So you will train your translation model on a bunch of these collection of translations. So we call it a parallel corpus. And then you will apply it and to anything you want to translate. But in that anything you want to translate, there might be words that you've never seen before in training. And your model still needs to give you some translation for that. So you need to be able to handle new words or very rare, not very frequent words. So what we do for that is a strategy called subword modeling. It's actually used in many areas of NLP now, where we split words into subwords. So we split, for example, poutine, we could split in put and in. I don't know if that would make any sense, but we could do that if it made our modeling a little bit easier, because then perhaps we would find similar related words that would map to the same vocabulary items in our model. And then there's this whole issue about that language can be quite figurative, translation can be quite figurative, and in the end, we don't actually want to have literal, over-literal translations of single words. We want to translate the meaning of the whole input, and that's quite challenging. And we don't have like a technical solution for that. We're rather just hoping that if we feed the model enough data, it will pick up certain connections that are perhaps more abstract. Okay, so a transformer, I guess you all know, but so it was originally proposed in 2017, and so we're using in translation. That's the state-of-the-art architecture that we're still using with slightly modifications, and you can scale it up or you can scale it down depending on your task. So we're an input and an output, an encoder and a decoder, and in the encoder, we're basically encoding the input embeddings into contextualized representations. And then in the decoder, we have the task of generating one output at a time, one word at a time as part of the translation. So first we would start generating code like we saw in the example, and then we move on. And whenever you generate something, you'll feed it back into the model and predict the next token or next word. The problem here is that while like when you use the model for translation, for inference, you would do that one step at a time. But for training, you can actually speed this up. You can parallelize this because you already know perfect translation. So you can feed it in at once. By shifted to the right, that means that in the first position, you will receive a starting symbol, and your model will be trained to generate the first actual word. And then in the second position, you will feed in the first actual word and predict the second actual word. And like this, you can parallelize the computation here, which is quite nice, which speeds it up a lot during training. But we need to take care of the attention. So we're adding a mask in the multi-height attention so that at the prediction of the second word, for example, we don't allow the model to pay attention to the future words that it still has to generate. And here, with the part that the encoder doesn't have is the attention, the cross attention to the encoder. So it connects all the, for every output word it creates this connection to the words in the input or to the representations in the encoded inputs. So during training, we can train it with maximum likelihood estimation, and we can see this as a conditional language model task. So we predict the next token, the next word in our output sequence Y, given the whole input sequence, so the input to the model, our X, and we do this one by one. So during training, we condition the prediction of the next token of the previous reference tokens. And during training, during inference, when we deploy the model, when we use the model for translation, we condition it on the previously predicted tokens. And so this conditioning of the previously predicted tokens that come from the model means that you have some kind of a search problem, because dependent on the choice that you made in the current step, you will have different outputs from the model in the next step. So we usually use greedy or beam search for that. I will just show you a quick example, because this is inference during translation is very important, and it can improve or decrease the quality of the translations that you get quite a lot. So beam search, the idea is to keep the k most likely prediction sequences in each step. So you don't only use one, don't only feed one prediction back to the model to see the next options, but you actually parallelize this and use the k top predictions and feed them back into the model and see what predictions you get out of there. And from then, again, you choose the k highest scoring hypotheses or prefixes and feed those back into the model, so that in the end you can still have a choice between k different outputs, and you can take the one that has the highest score. So here in this example, it's a very small example. So we start with a beginning of sentence symbol, and then we ask the model to predict the output probabilities for all our vocabulary. Vocabulary here is just 3 tokens, A, B, and end of sequence. So we get a model score for all of those. Here, that's the log probability. So higher is better, or less negative is better. So here, the highest scoring one would be B. And in greedy search, we would only feed this back into the model and continue. But in beam search, we would, like in parallel, feed both A and B and see what the next predictions would be. So again, we'll get output probabilities for all the options in the vocabulary with the output scores, and then we can combine those 2 scores. So we just multiply them and can compare all the 6 options now, which of those are the best ones. So it's A, B, and B, B. and we can discard the rest, and those two will feed again into the model. And in this case, only one token gets all the probability mask, which is usually not the case, but in this example, it's the end of sequence symbol, and then we have the final score for one sequence A, B, and one sequence B, B, and the end of sequence symbol, and we can compare the scores, and we pick the better one, but we still have a second best option there. So this is how our inference works in state-of-the-art models. And you can see it's, if you think about scaling this up, so usually we have models that have 30,000 words in the vocabulary. That search is covering quite a large space, even though it's still a small, it has to cover quite a wide space. And you can imagine that if you make an error in that search, then it can affect the quality of the model quite drastically. So I mentioned another thing before. So I keep talking about tokens or words or subwords. So here I just wanted to emphasize again that we're actually not modeling words anymore, but we're modeling so-called tokens. And those tokens can be words and can be parts of words, can be characters, can be, and that's like the basic unit that we feed the model and that we build our vocabulary over. So from the example sentence that we've had before, we could say, okay, we split it into tokens at every white space, and then we would have 4 tokens, and we would observe each of them once, so we'd have 4 types, so 4 unique types as well. But then you could also say, well, why don't we split at punctuation, and then we would have 10 tokens from the same sentence and 8 types, because k occurs 2 times, and also the apostrophe occurs 2 times. So that you have one sentence and you can present it in multiple ways to the model. And you can see that based on that, you'll have different challenges. So this will, if you use that kind of punctuation splitting, you would have longer sequences, but you would have fewer types in relation. And if you use this white space tokenization, for example, you'd have fewer tokens, but a high type into token ratio. So what we're usually doing is going for more aggressive splitting, because that increases the frequency of observations for most of the words. So for example, here you would be able to learn something about cohere and combine their semantics that you learn about them, while here you would have to treat them as separate instances, and you might not be able to make the connections between their semantics. So state-of-the-art uses subwords instead of words. And instead of asking linguists, how should we split the data, we usually do this statistically. So we use frequency-based automatic segmentation. There's 2 famous algorithms, the BPE one and unigram language modeling. And the most frequently used toolkits for that are SupwortNMT and SentencePiece. They both have Python, SupwortNMT is a Python library, and SentencePiece has Python bindings. And this other thing I wanted to mention is role of data. So we already spoke about size before. So Sylvain had this nice plot of billions of parameters. I'm talking about like even a Bayes translation model, so a small one. The original Bayes transformer had only 65 millions of weights, but that's quite a lot if you think about parameters. If you think about what could, like the capacity, the things you could learn. So a question that comes up very frequently is how much data it would need. Like how much data do you need to build a translation model for your language? And the answer, as often, is it depends really. It depends on the pairs of languages that you're modeling. Are they very similar? So for example, French and English share a lot of structure. They're relatively similar. And then if you, for example, translate between French and Chinese, you would have 2 different scripts. So they would share less vocabulary items. The structure is completely different. You would have different realization of phenomena, linguistic phenomena. So it really depends on what your language pair is, and also what kind of quality are you expecting. Are you translating, and are you translating a letter to your grandma, or are you translating a legal document? So it really depends on that kind of setting or in these kind of conditions. But usually, like the rough estimate is that once you have like 100,000 sentences or pairs of sentences in your specific domain, you usually can expect some decent quality if the data is okay, but it won't be perfect, and more is usually better. So often in practice, we just take all the data you can find, because the ceiling is often not reached. But there's also lots of recent approaches on using unsupervised data for machine translation, doing data augmentation, for example, so back translating, using dictionaries to enhance or to augment data. You can use pre-trained embeddings as well, or you can do multilingual modeling, where you combine the data of multiple languages, and that helps specifically if they're related or similar or share, have like some similarities. Yes, and evaluation is like tricky too, because how can you tell whether your translation model is good or not? So here in that example, I gave you 5 options, and that could be the output of a model. And if you read through them, yeah, it's quite tricky to rank them or to score them, because each of them is not perfect. It has their own issues. So the 2 metrics that we usually use are automatic metrics. So we use them for development. So we make use of reference translations that we have, and then compute basically a matching score between the outputs and the reference. And based on the metric we choose, we'll get a different answer. So here I compared scores for BLEU and character F-score. So usually you would compute those on the corpus level. So for the whole test set of translations, here just for illustration, I use it for sentences. And BLEU is based on precision metrics on n-grams of tokens. So it would count basically the tokens that are overlapping and computing n-gram statistics, or precision based on n-gram statistics about them. And then for character F-score, it would be character n-grams. So you would look on the character level. So here in the example, you can see the first option would be the highest scoring output according to both of these metrics, but we see a drastic difference here, where BLEU would rate this translation as really low, even though it's kind of a masculine protein. I don't know if that word exists, but if that would make any sense. But it could happen to like a language learner like me getting the gender wrong. And then character F-score, because it looks at the character level, it will not penalize it so hard, because there's only 2 E's missing basically. So there's different perspectives you can get if you use different metrics for evaluation. Yes, so that's the wrap up about like quick recap of concepts that are important in translation development and research. And now I want to swap over to JoeyNMT. So this is a toolkit that I built together with a friend when we were both in our PhD, and we really needed a toolkit to work with. And now Mayumi Ota and other students at Heidelberg University, and also JoeyNMT contributors from all over the globe are continuing the development. So the problem that we were in back then is that a lot of code for NMT is online. So you'll find NMT toolkits for all kinds of deep learning toolkits. So it started with Theano, but now you find a lot of them for like even different ones for PyTorch or TensorFlow as well. In addition, there's free compute through Colab, and data is also freely available. So you'll find parallel translation data freely for download on the web. So in principle, it seems quite accessible. You can get started very easily. But the problem is that the code that is available online is not always easy to use. And as a beginner, if you come into the field for example, in your studies, or if you start with your PhD and you would under research in that area, it's hard to get started because code bases are changing, because code bases are big, they're not well documented. It's unclear how data gets fed into it. And if you want to make a modification, where would you start? So the solution that JoeyNMT is that it's a clean code base. It's minimalist, so it doesn't contain a lot of things, but it contains the most essential things, and it's well documented. So it's much smaller than other toolkits. So I think in the beginning, when we published our paper about this, we did a count of lines. It was like 2,500 lines of code, while the smaller of the bigger, more popular toolkits that were available at that time were at least 10,000 lines of code. So at least 5 times smaller, but it still covers the core features. So we went for like an 80-20 approach. So it should get at least 80% of the quality and cover 80% of the features, but with 20% of the complexity. So we made the API quite, we reduced a lot of abstraction. We also did a user study on how fast you can learn to use it. For example, pre-trained models, tutorials, FAQ, and so on. It's based on PyTorch, which is quite user-friendly. But most importantly, it does not do everything. So it only does translation. It doesn't do any other NLP task, and it does not grow much. So since the beginning of when we published it, there's been a few pull requests, but the basic API has not changed, and it's still valid, still works, still gives you on most of the tasks the baseline performance you want or that you need in order to publish a paper if you build something on top of it. So yeah, that's the nice part. And in order to find out the features, we compared the toolkits that were out there and try to identify the basic set that we need. So you can train RNN and transformers. You can work on CPU, GPUs, has some monitoring of the training process. I'll show you what you can do, basically. But what's very nice now is that after some time, people started publishing their extensions to Joey. So the core stayed, but people could publish the extensions. So for example, we have a reinforced Joey that implements a bunch of reinforcement learning algorithms, and you can share and load pre-trained models as well. So for example, for the Masakane community, we provide over 30 translation models for African languages that you can just load and use or further train or use for your NLP research. Yeah, it is comparable in terms of quality. It's not as popular as other big toolkits, so you can hear some GitHub statistics. It has been used quite a lot in recent research. So over since its existence, it has been used in research as well, not just for beginners, but also for, well, when you want to implement for quick prototyping in research. It also helps to have a small code base. It might not be the best choice when you want to replicate another paper exactly, because it's better to use their code. Non-sequence to sequence applications are a bit harder because you have to change the architecture. If it's a classification task, it should be fairly simple, but yeah, you'll have to take the code apart a little bit. It's not optimized for speed. It has a few things like floating point 16, precision, but we didn't really tune it for speed because it was more important to have easy access to the code and make it readable. And then you can also not load BERT at this point, so it's not so much for fine-tuning or for transfer learning, but really just for training translation models. So off to the demo. So I'm going to switch tabs here. So I started this roughly in the beginning of the session. So if you started your Colab now, you'll probably see something happening here. So just
could you please make it a little bit larger? Can you zoom in?
Yes, that's a good idea.
Thank you.
Okay. It's a little bit too big. So you can find that on GitHub, and it shows how you install and use JoeyNMT and what you need to do for your data to feed it into it. It doesn't show how to modify it, but you could also load the API, different API parts into the Colab and modify it in there and train your model by calling the different functions. So here that's just about installation. For the data, we are going to, for this example, I will use English to Esperanto. So Esperanto is a constructed language. It's very similar to a lot of Romance languages. So if you know any Romance languages like French or Spanish, you'll probably be able to guess a few of the sentences. And we're going to download them from the Tatoeba challenge. So Tatoeba is a website where you can submit translations in order to help build a corpus, a dictionary for your language. So the sentences submitted there are not so complex, so it's a rather easy domain. That's why we can build a translation model from that in relatively short time. And this example, we'll use 400,000 sentences. And so here in the beginning, we're just downloading it and unpacking it. And then here's an example of the data, how it looks like. So we'd have two files, for example, from the dev set, the English side and the Esperanto side. And then you would have the lines. The first line would contain the Esperanto translation of the first line in the English file. So you can see some examples here. and you can guess a little bit what different words mean. So this is the format that we'll use. You can see how large the data sets are. We'll use a subset for testing and evaluation, just 1,000 examples, because that takes a little bit of time when we're evaluating. And for training, we'll use 400 to 1,000 sentences. And then as a next step, we'll do the subword modeling, the breaking down of words into subwords that I presented before. So for that, we're going to use the JoeyNMT library. So again, we're setting a few file paths, and then you basically have to call this learn BPE function. That means it looks at the training set, what do the character frequencies look like, and it proposes splits, or it outputs the splits that should be used to split this corpus. And here we're using 4,000 of character merges to build that final set of vocabulary. And then with that, so the file that it generates looks like this. So it contains a list of characters that should be merged if they occur next to each other. And then we use those to pre-process all the data, so the training, the def, and the test data. And that's what they will look like afterwards. So same examples from before. You can see, for example, in English, some is split from things. So whenever there's this add, you know that it's split. And then you can see that very frequent words are words. So need occurs a lot. So it will be the character combinations will be very frequent, but so it will be treated as it is, as a normal word. But then not so frequent words like cards will be split into C and arts, because maybe arts occurs with yards, for example. And it doesn't necessarily make a lot of sense. Like C add doesn't necessarily have to have a separate meaning, but the model will observe it in different contexts and hopefully construct meaning from neighboring words. And then on the Esperanto side, you can see as well here the very frequent words like me, for example, means I guess, will not be split, but then other words will be split. So this is what the data looks like when we finally feed it to the model. And also when we use the model for testing, we'll also have to split any input like this, because otherwise the model, it will not be able to map it to the vocabulary. Okay, and for preparing the vocabulary, that is a file that contains the indices or contains basically just collects all the vocabulary items that we'll have. That it will define the options we have in our softmax. So what are the output tokens that we're working with, and then we're defining the whole model configuration. So it's a config file here. It's a little bit ugly because we all put it in one string, but on the JoeyNMT repository, you can see some examples for some benchmarks. So either as a SLT translation or WMT for English and German, for example. And so you basically have to specify a few data paths to the data that we just prepared. And you have to tell it, okay, I'm modeling on subword level. You feed in the vocabulary files. Then some testing parameters. So we'll use a beam size of 5. So the example I had before, we'll consider 5 hypotheses at every point. And we'll use Sacre Bleu for bleu computation. And then here are some hyperparameters for training. We'll use Adam optimizer, cross entropy training, learning rate, and so on. We'll train for 30 epochs. You can train longer if you want to. And we'll use blue as an evaluation metric. And then for the model, you specify how you want to initialize it, what kind of encoder. You can use here either recurrent or transformer. It's a pretty small transformer, so it has 6 layers, 4 heads, relatively small embedding size. Yes, and that's how you specify, that's how you tell Joey what to do, basically. And yeah, you can find a lot of those online. And during training, JoeyNMT will write TensorFlow logs. So you're loading the TensorBoard here. And if your model already started training, you'll see some diagrams popping up here. So this is the tracking of the training loss. Well, it's not optimal to display, but you can see the validation loss is going down, the perplexity is going down, and validation score is going up. Yeah. display is not the greatest in Colab, but you can also externally run it. And then this is the command line interface for training, setting the training. So you'd pass the configuration file that you wrote to Joey in train mode, and I'm just going to scroll up, still training. I'll stop it. So you see what's happening. So first we'll log all your parameters. It will tell you, okay, this is the data size. Well, actually, because we specified a maximum length of 30 sentences, it will filter out all the sentences that are longer for training. So it's a little bit smaller even than the whole data set. And then here's some training example just to verify that this is actually what you want the model to train on, and some excerpt of the vocabulary. Yes, and then this is the training log that you will see. So you see the batch loss, it should go down, some reports on speed. And then once in a while, we're doing validation on the evaluation set. And if we get a new high score or new low score on perplexity, we will save the checkpoint. So you'll always have the latest checkpoint. The latest checkpoint will be the best model you've seen so far. And here are some examples of the initial model output. So this is the source sentence. This is the reference of what it should have generated. And well, in the beginning, after the first epoch, it's not great yet. So it says, I don't know you instead of I made you something. But at least it got the I and the you right. Well, the next one is pretty terrible. It said thank you instead of twice 2 is 4. Then in the next one, well, at least it got like the exclamation mark right. And the last one is just not going very well. So you can see the blue score for this is 1.5. It's very low on a scale from 0 to 100. And then you can like follow up on training how it's improving. So you'll see, it's quite interesting actually to see how the intermediate outputs are changing and getting better. So at that point, after 8 epochs, it translates the first part of the sentence at least right, and it gets the sentiment at least right of this one, like where it says that hurts, stop me. It said it's troubling me. Well, it's something. So it's getting better. So that was a blue score of 16. And I want to show you the outputs that the model is generating. So here you'll have the model directory, and you'll find intermediate hypotheses here. They will be saved as a file, so later you can do some analysis with them or so. You'll find checkpoints. You'll find the configuration that you use for training, so that later you can load it again or check how you had set your hyperparameters, the whole training log, the translation log, once you're done testing. And you can also see the vocabulary that it actually used. Yes, so let's scroll down a bit. And then I also provided some code here for reloading from a checkpoint, because sometimes if your Colab disconnects, you want to continue training later on from a checkpoint that you have to download first and then load again. And there's also a translation or a test mode where you, if you call that, it will just test the model on the test set that you specified in the configuration. So it ran that one before. It got like 24 blue after probably like 1 hour of training. And here then, okay, it's it's actually in a translate mode. So the translate mode is a bit more interactive where you can play with your model. So I just wanted to have an Esperanto sentence. I got that from Wikipedia. So I pre-processed that with the BPE splits, because I need to do that, because otherwise the model, it's not aligned to the vocabulary task. So you can just paste that here, and then you can ignore the warning messages, and you'll see here the translation. It's not perfect, but it was also not trained on Wikipedia. But you can kind of see what the model can do and what it can't do. So it gets Esperanto right, and then it gets something about language, the most recent international language. Oh, yeah. It's okay. It's not too bad. But yeah, this is basically one run. I can stop this now. Through the capabilities that, yeah, how to use JoeyNMT. If you look into the code, we try to make it as simple as possible. yeah, and it is growing. Like functionality is added, for example, by Yumi implemented loading embeddings and multi GPU training. So there's slight improvements over the years, but they're not so major. But the really cool stuff about JoeyNMT, about open sourcing your toolkit, is that other people will use it and they will probably build something that is more useful than what you have built with it. So for JoeyNMT, it's really cool that there's 2 grassroots research communities that have adopted it or have started building model with it. So Masakane, which builds NLP for African languages, they have over 30 or 40 translation model for African languages where there's no translation model ever before. So it's pretty cool. And Turkic Interlingua is looking into NLP for Turkic languages, and they also use JoeyNMT because it is easy to get started with and it's easy to expand. And there's also some extensions of for research projects or from some of my students. So my favorite one is the reinforcement learning one because it has this beautiful logo that is totally on point. And there's been extensions for sign language translation, for speech translation, for image captioning, and you can also use it in the Slack bot, for example. And we collect all these extensions in the JoeyNMT README, so you can go from there and explore how other people modified the code and what they added. For example, if you want to have image encoders, how would you add them into the architecture? Yeah, I also put a bunch of material here for getting started with neural networks. So if you download the slides from SlideShare, you can click on them about neural networks and NLP, neural machine translation, and a few JoeyNMT resources as well. There's Masakane has some notebooks online, and there's also YouTube tutorials. And yeah, happy to take questions now. And thank you for being here, listening.
Thank you so much, Julia. It was a great talk, and I love how much impact this framework is already making with the machine translation models for the African language. You mentioned there has been none before, and so I guess it's always great to see when something you work on has such an impact. That's awesome. We have a few questions from the audience, and I'll start with with one of them.
Yes.
So, since a few weeks, I've noted a big improvement of Google Translate, which seems to have catched up on DeepL. Is it possible to share a bit of the secrets? I guess because you work at Google, people want to know all the
yeah, sadly, no,
details.
I'm not here to share secrets. So yeah, we're currently we're constantly trying to improve the quality of Google Translate, and there's a lot of processes that go into it. But as well as DeepL is keeping their secrets to themselves, I can't tell you exactly what we're doing and whether we have caught up with them or not. So
Yeah, that's understandable.
Finding improvements. It's good. It's good.
If there are secrets, there are apparently a whole bunch of lawyers protecting those secrets. So they should remain secrets. Another question is, how does many-to-many translation systems work inside? Is it a general model for any pair of languages or a lot of pairwise models?
Mm-hmm. So you probably, technically you train the same parameters on it. So you would give it hints about which language there is in the input and is expected in the output. So you usually use language tags, identifiers that say, well, this is an English sentence, this is a French sentence, and please translate this to, or more importantly, translate this to that language that I want. So you would give the model hints, but the parameters would still be all shared. So technically, you can say, well, it's one model that does it all, but internally there will be some clustering, or not clustering, but there are some papers that look into how that visualize the embeddings, the representations, and how they are grouped and clustered. And there's also some papers on a recent paper on looking at how the representations evolve over the layers. So which layers, like how language specific they are. So there's a lot of analysis on that. It's not simple. You won't find that group of parameter that only does one language and the other one of the rest of the parameters only does that language. It's not that simple because we're all training it end to end with gradient propagation. So there's a lot of influence from other samples too. It's just one model. So but there's a lot of interesting research going on in that space. Yeah.
Mm-hmm. A couple more questions. So when fine-tuning a model on a dataset, should we also fine-tune / retrain the tokenizer so that our vocabulary would include the new words?
Yeah. So if you use a model that was built on a different vocabulary than you want to use afterwards, then you need to do some adaptation. So you can either try to build some kind of mapping between the embedding spaces, or you'd have to do some bridging between vocabularies, because the vocabulary, the segmentation is that results from the segmentation is the most basic, like the first bridging gap or the first technology that bridges the gap between words and the model representations. Again, there's research on that. There's like one of my colleagues worked on that specifically, and he came up with a method to bridge this and to have expanding vocabularies. It doesn't, like, if you have new data, you can use the same you can use the same segmentation algorithms with the same splits, then that's better. But for example, if you have completely new script for a language that you're adding, for example, this requires being more creative with the solutions and doing more adaptations on the vocabulary matching side.
And when you say more creative, what do you mean?
I mean that you can't just feed it in and hope it will train. You'll have to write an algorithm tailored to the vocabularies that you're dealing with. And depending on how well that goes, the quality of the model will be good or not. So it affects the whole pipeline quite drastically.
Makes sense. Another question from the chat is about PyTorch. So since JoeyNMT is built on top of PyTorch, can those models be visualized like other PyTorch models or exported?
We haven't actually done that. So yeah, it would be interesting to know what kind of models you're interested in. I can't talk to you right now. I mean, it's PyTorch. You can store the parameters in a way. They have names, so you can probably infer where they belong and where other model parameters belong. Yeah.
And I had one question from my side, kind of as a maintainer and contributor to that library, which kind of is different from what I think people are typically expect from a library, right? To be sort of production grade, to have all the features that they need. The goal is to be more like educational. So how do you, as a maintainer, sort of balance those requests? Let's say there's a few requests to add kind of latest and greatest advancements from some kind of paper, but at the same time, you still want to keep it, I guess, friendly for beginners.
Yeah, that's a good question. So we didn't have that many requests because we made it so explicit that the purpose of the toolkit was not to do all of this. But of course, sometimes people ask, why is that not there? And then, well, what we can offer is we can try to help you implement it, and we can try to help you find other libraries that do it and try to figure out how hard is it to bring that into Joey. And it should not be that hard if the paper describes the method well, or you have some other code to guide you. But yeah, it's a bit hard to say no to these things, but it's also necessary to make the code useful for others. And there's enough code on latest state-of-the-art extensions. So usually when you're at the level where you really want to work on top of the latest method that was published just 2 months ago, then you'll probably be able to process a more complex code base quite well. But you can still you can take JoeyNMT as a beginner. You can read through the code. You will find the same structure of the code the training loop, the pre-processing of the vocabulary, the padding, the batching. You'll find the same principle as in other libraries too. So hopefully I know it's easier to move on from JoeyNMT to a more complex toolkit than just starting with a complex toolkit right away.
Okay, thank you.
I have one more question, and I promise it's an easy one. Why is it called Joey?
Oh yeah, so there's this tradition somehow that new machine translation toolkits are named after animals. So there was Nematus because it contains N, M, and T, and there was Neural Monkey. So we thought it had to be an animal, and it had to be a cute one because it's supposed to be friendly. And we were in Australia when we had the idea, so koala babies or kangaroo babies, marsupial babies seemed quite a good option for that.
Yeah, that's a cute name. I think thank you so much. It's been a great pleasure to have you present, and we hope to see you in person when in-person meetups are possible. And I'm gonna pass it on to Alex to introduce our next speaker.
Right. So next up, we have Shubhanshu, who's an ML researcher at Twitter. He's working on content understanding research team, and he finished his PhD on information extraction from digital social trace data with application on social media and scholarly communications data at iSchool University of Illinois at Urbana-Champaign. His current work is at the intersection of machine learning, information extraction, social network analysis, and visualizations. Right, Shubhanshu? Take it away.
Okay, thanks for having me here. Let me just share my screen. Okay, hope my screen is visible now, right?
Yep, that's great.
Okay, great. So hello everyone. Yeah, I'm very excited to be here, and thanks for inviting me to give this talk. I'm a NLP researcher at Twitter, and before that, I did my PhD at UIUC. And most of the work I'll be presenting is from my PhD time, just like the JoeyNMT work, which was presented for me, a lot of it. Yeah, let's get started. There are a few links I have shared in the slides, and also I have shared the link to the slides with the organizers as well as some other links. So yeah, you can look at it. So let's get started with the agenda. So I'll mostly be talking about first of all, the importance of information extraction for social media text, how it differs, and then I'll talk a little bit about what are the various ways where we can actually improve social media information extraction. And then I will end it with something called digital social trace data, which is a concept I came up with during my PhD to encapsulate different types of data set which are beyond text and how you can work or do analysis on those types of data, including the text as well as other attributes. And I will give you some specific use cases from social media data, as well as some examples from scholarly data, which is also a type of digital social trace data. Okay, so let's get started with what I mean when I talk about information extraction tasks. Oftentimes, you can think of information extraction tasks at these three different levels. They should have been these tables, but the first is token level tasks. So that means here the labels are tokens in the document, and then you have to assign labels to each token. The next is document level task. That means you have to assign some label to the whole document. And the final one is our corpus level task. That means you take a corpus and then you assign certain properties to those corpus. So for example, the corpus level tasks are slightly harder to perceive, but there are examples of, say, key phrase abstraction. You are given a large number of texts, identify what are the most important key phrases in those whole collection, or taxonomy construction, which words are related. So car is a type of an automobile, a Ferrari is a type of car, those kind of things. And lastly, like, things like topic modeling. So these work on a collection of documents, not just on, say, like individual documents. So why social media information extraction is important and also challenging. So one of the main thing which also like some of the previous slide which you like previous presentations you also saw is that most of the work on natural language processing on information extraction often happens on like regular data sets like Wikipedia data sets, which are like very well formed, formally written, or newswire data sets like Reuters, New York Times. And for example, like I work a lot on named entity recognition. So like one of the most popular data set for named entity recognition is the Cornell 2003 data set, and that is derived from Reuters. And like most of the models you will see, they just like test their benchmarks on this data set. Also, additional new data sets which are coming these days, like oftentimes like things like Glue or any other like additional NLP tasks, they often derive from some of these data sets and also are like either based on Wikipedia or some of these type of formally written corpora. There are very few examples of data sets which are for social media. In fact, there are a lot of social media data sets, but often they are not used as much in research or like in like mostly like because I work on the research side, like mostly in research papers. So I will also talk about like how to find them and like how to use them. And when I say social media, I mentioned like data sets which are derived from, say, like Facebook comments, Facebook posts, Twitter tweets, or Reddit posts, and all those things. Next, like another reason why social media data is challenging is, unlike, say, the normal news data sets or like some other, like, say, Wikipedia data sets, social media data set actually has a lot of inherent structure in it, which provides a lot of context. So, for example, like the simplest one is like the structural difference in how you write, say, tweets or posts is like you can mention people. And then like these mentions of people, these are like structurally very different from, say, how you mention named entities in a normal text. So now you can directly say @Shubhanshu and like then you continue your rest of your message. Secondly, like you have other topical attributes like hashtags. Then there is a broader context, which is like you have threads. So like oftentimes you usually, if you go to a Reddit post, you have like a comment thread, or if you go to a Twitter post, you see like again like Twitter threads there. Again, they are often less formally written, as I mentioned. Again, like we do see both types of writing on social media. So some people do write like very formally, and some people also like write like a slightly less formal language. And that makes it very challenging because that increases the diversity of language on these platforms. And this brings us to another issue, which is like a lot of unseen words, which is like, so social media language evolves quite fast. So like you are very likely to see a lot of new words. So for example, like the word like kofifi, which got trending, I think, like a few years back. It will not exist in like most of the NLP corpora and like even for social media, but suddenly it exploded and its usage was much more. So if you train any model after that word occurred, like your model is going to capture those words.
Sorry, Shubhanshu, I think there's a little bit of noise coming from your mic that a few people noticed. And
okay. Is it? Let me just check if my mic is. Cam and mic. Hello.
Yeah, we can hear you, but occasionally there's some noise.
It's probably just hanging and touching the fabric or something every now and then, and so that.
Oh, okay.
That's why.
Yeah, I've changed my mic now to my laptop mic. So is it better now?
Yes, it sounds much better. Thank you so much.
Yeah. Okay, thanks. So yeah, like, so let's give an example of what like a challenge is. So for example, there are a lot of models or tools which are already trained on the general purpose English data sets. And there was this paper which tested, like evaluated how these models perform on social media data set. So mostly like this data set is derived from tweets. And as you can see, like, the performance of things like, say, Stanford NER was not as good as like something which is more specified towards, say, social media data sets. And I will show you other examples where like I've found like similar cases where like a social media trained data set is much better performing than a normal use-wire data set. And this is also expected because like, it's a simple example of domain shift. But the problem is like often when practitioners use, and when I say practitioners, I mean people who are not necessarily, say, machine learning modelers, but these are people who just want to do some analysis and they want to, say, find all the named entities in a bunch of tweets. So what they will do is they will directly go to some of the more popularly available softwares and then try and run it on their data set. And the biases from these data sets will directly transfer to their analysis. And when I mention bias, I mean bias more in a simple statistical sense. That means like just error propagation, that like you made a lot more error just because the data set was like a social media data set. So the key message is like, we need social media specific models to perform well, and we need them like, publicly available so that like other people can use them. So I will talk a bit about like a tool which I developed, which is called Social Media IE. It's also linked in the presentation, which basically just allows, it is trained on a collection of social media data sets, and it allows people to have outputs from these social media models for any of their tasks. So it's more aimed at like, if you are analyzing a bunch of tweets or like, say, a bunch of social media posts, you can use this tool instead of, say, something like, say, Stanford NLP or some other like regular newswire corpus trained data set, and you're expected to get better outputs. It comes in two flavors. So like it has like support for text classification as well as sequence tagging. One important thing I want to highlight here is that you see these multiple outputs. And as I'm going to talk about later, this is a multitask model. So it's a single model which gives you all these outputs in one go. So it also reduces like the computational burden for people who just want to do some analysis and not like get into the modeling aspects. So what are some application of information extraction? You can use it to index your data set. So let's say you have a collection of social media posts. You want to create a search interface for it. You can do it like, say, maybe based on entities. And then like you can use those entities as an indexing approach for the posts. So now coming to how to find those data sets. So initially, when I started doing my research, it is very hard to get access to some of the publicly available social media data sets because like some of them are like mentioned in a paper, not many of them are cited. So my first work started actually by like creating a collection of publicly available social media data sets. And that resulted in something called the metacorpus, which I call like social media IE metacorpus, which I'm going to give you a show. It contains a collection of, I have lost the count because I keep updating it every day, of like more than, I think, 100 different data sets. Now, these data sets are specifically generated based on social media data, and it has like, they are divided between tasks. So for example, classification tasks, tagging tasks, named entity recognition, translation, machine translation, entity linking. And then it also has like access to like some other like, so the first one, like most of them, like because most of the research actually happens on like either tweet or Reddit based corpus. So like those are the corpuses you are most likely to find annotated. But there are also examples of like, say, Facebook, YouTube, Reddit, and Gap corpuses, which you can use for like doing the analysis or doing the benchmarking. Now, of course, these are large number of data sets. So the way I have worked, so when I was working on my thesis, I had to simplify it a little bit to a selected few, which can serve as a benchmark for certain classification or sequence tagging tasks. So I created this benchmark called the meta corpus benchmark, which has around, I think, 10 text classification data sets and 10 sequence tagging datasets. So, and then I say sequence tagging includes part of speech tagging, NER, chunking, and supersense tagging, and for classification, sentiment, abusive, and uncertainty, which includes a bunch of other types of tasks. So going back, so now just to give you a breadth of what these datasets look like overall, we have a large number of, I think, more than 100,000 posts with an order of that, a number of tokens for tagging data sets. So this basically, one of the major issues is if you want to train a good model, you need a larger data set to train the model. So the way I was approaching it is okay, why not take all these different data sets and train a single model? It increases the number of training data available, and then it allows you to share information across all these data sets. So these are list of tagging data sets as well as classification data sets. So this really increases the amount of training data available for training social media models. So now let's come to, so before I move forward, I'll just stop to take any quick questions.
Yeah, I don't think we have any questions at the moment.
Okay, great.
Yep.
So I'll continue then. So now let's move towards the main idea. Okay, we have these data sets available now. How can we improve the social media information extraction process? So I will talk about a few different approaches: rule-based models, multitask learning, multilingual models, and active learning. So the first one, and this is, I'll talk a bit about a very old model. There were days when people did not use neural networks too much. Word embeddings were the new thing. So it's a model from 2016. It still works very well. And the approach is that you can often utilize the task of named entity recognition, where you want to identify names of people, person, people, location, an organization. You can often perform that task using a collection of features, which are either based on gazetteers, which are publicly available. So you have things like Wikidata, which gives you a large number of names of people or large number of names of organization, which you can use it to generate features for each token. And then you can use regex-based features. And then you can combine it with word clusters and word embedding. So word clusters, for people who have been doing NER for a long time, they know they used to be one of the strongest features for doing named entity recognition. So you can again train your own custom word clusters on social media data and use it to improve your model. So this is a model which we developed 2016. It still is often used by researchers and practitioners, and it performs very well on social media datasets, particularly tweets, because that's what it was trained on. And just to give you an overview of the types of supported tags in this model, we have basically company, facility, geolocation, movie, music artist, and so there are 10 different types. And the model gives a pretty good F1 score of around 59% on a collection of some of these types. In an independent review by the Human Geo team, which they also published as a blog, they also find that this model performs pretty well compared to, say, Stanford Core NLP or OSU, NLP, or some of these other publicly available models. And because like the way we made it, it's like very easy to retrain it on your own new data sets. So they tested it and found that like it's you can like further improve the performance of this model by retraining it on some of these additional data sets to get like a very state-of-the-art performance. Next, we talk about multitask, multi-dataset learning. So again, like multitask learning is very popular these days with the advent of deep learning, because like now you can actually have different modules and you can combine them to learn like say shared representation. So the next step, like, so this was very like a non-neural model, which I presented earlier. Now I wanted to investigate with a neural network-based model. And the key idea was that like we have all these different data sets with us, like can we use them together to improve performance across all the different tasks which we have. And as I mentioned, like for tagging alone, we have like around 4 different tasks. So the way I did my evaluation was like you have a single task, single data set format, which is just take a single data set and train it on its own task. And that serves as a benchmark. Then I had a different formulation, which is multi-dataset or multi-task approach. So now this is slightly different. Oftentimes what happens is, like, let's say you have an NER model. You are going to, and if you can find 5 different datasets on NER, not all of them are going to have the same labeling schema. Some will like annotate only person, location, organization. Others will annotate like 10 different types of entities, as I showed you before. So what you can do is then you can have all the datasets which share the label schema. You call them, I call that training under the umbrella of multi-datasets. So they all share a head, the output head. And then if you have multiple datasets for the same task, NER, but now they have different labeling schema, then they have different heads, and then you can still share the representation across them. And then you can do it like in a more stacked fashion also, that like some lower layers like perform some lower level task and some higher layers perform higher level tasks. And using this approach, I was able to develop like multi-task models, which are like perform like one of the best for across all these different tasks for sequence tagging. And also I'll show you later like the same for text classification. And this really like helped us improve the performance on like the named entity recognition tasks, which was like a very challenging task, especially like say the 2016 dataset is like a very challenging dataset to get improved performance on. So how do we do the training for these type of models? The idea is pretty simple. In a traditional multitask setting, oftentimes you have a single instance which has been labeled for multiple tasks. But again, given the nature of how my whole training, like the collection of trained datasets was generated, it is very hard to have like the same sentence being annotated for 5 different tasks. So you can't do like say like loss aggregation from all the different tasks for the same instance. So the way like we approached this problem was like you create like homogeneous mini batches. That means one mini batch only for one task with the same label schema, and then you compute the loss for it. And then you sample these mini batches like iteratively from these different data sets and different tasks. And then you just do your normal loss transfer. So if you think of it like basically if there are multiple heads, only at one head, like in one batch, only across one head, the loss is getting propagated, like the errors are getting propagated. And this allows us to like do like easily like include additional data sets and additional tasks, and you can like continue training. The interesting thing now, which comes because of this approach, is if you look at this shared representation. Now, this shared representation, so in most machine learning models, what happens is the shared representation, you do a dot product of that shared representation with the label embeddings, and then you get the score for each label. So effectively, like you have a matrix where for each label you have the same size vector as the shared representation, and you can consider them as label embeddings. And the interesting thing, which I found as part of this model after training, is even if you have these different data sets, so these are all part of speech tagging data sets, they have different labeling schema, like one uses the universal dependency schema, one uses another ARC schema, and another one uses a Pentry Bank schema. So even when you train with in this fashion, in this multi-data set, multi-task fashion, the model automatically learns to identify that, okay, these collection of labels actually mean similar things. So like these are all the noun type of labels which are grouped together. These are all verb type of labels which are grouped together. Then again, another one is this is like pronouns, proper nouns, all the punctuations are grouped together. So this is very interesting. And when you extend it to say something like NER, which as I already mentioned to you, they are like 5 different types of labeling schema which I was using. And now when you see, like, again, the collection is like all the location, things like location, geolocation, facility are all grouped together. And then, like, say, all the O's across all the data sets are again grouped together. And another interesting thing which appears is that the direction from B to I. So often in NER, people use this BIO labeling schema. So this model automatically captures this direction that all the B's are on one side, all the I's are on one side. So I'm just using a TSNE projection here. And this is pretty interesting. And it also is applicable for things like chunking. You again have like a consistent direction for chunking. And then for supersense tagging also, like all the nouns are clustered in one area, all the verb labels are clustered in one area, and again, like the BIO are again like having a similar direction. The good thing about this library is also it has a web-based UI where you can input a text and you will get like this nice visualization, which allows you to compare all the different outputs which this multitask model does. So it's like good for like inspection of how your model performs. And because all the outputs are aligned, you can like do additional inspection or like analysis on it. Similarly, like I use the same approach on segment classification dataset also on the classification datasets. And again, like I had like a pretty good results for all these multitask models. Interesting thing again with the label embeddings was that we saw clusters like, and again, like here we have how many, like I think 10 different tasks, 1, 2, 3, 4. Yeah, eight different type of tasks. And the model automatically learns that, okay, these all labels mean something similar, like all the positives are in one area, all the negatives are in one area, even negatives are closer to hateful and abusive. And all the normal, like the middle labels are all clustered in one area. So this is like a very interesting thing. If you are working with any like model, like multitask model, it's a good way to like visualize, say, what the label embeddings look like. Again, like we have this directional flow on the embeddings, like that positive goes to neutral and goes to negative. So this is also like something interesting, which like I did not add any specific laws or any specific constraint in the model to directly model these things. But like this is something very natural. Now the model is learning these things. You can actually add some more regularization that, okay, these are all positives. So you can probably regularize the model by saying that align all the positives to have similar embedding based on this analysis. And again, as I showed you before, like this also has a web-based UI. So I'll just give you a quick rundown. I have linked a notebook here for this model, for this tool in the IC2S2 2020 tutorial website. The notebook is a collab notebook, and it will take some time to run. But I have also given instructions here on the same IC2S2 setup page on how to run it on your local setup. So again, like the main focus is to allow practitioners to use this type of model locally. And once you have this locally set up, so I'm actually running this model on my laptop, it has a very nice functionality. It allows you to get all the outputs in either JSON or data frame format. So you can just use the whole output as a data frame, and then you can perform your analysis based on like whatever you want to do. So like if you see, like I give a tweet as an input, and then the output is like basically a JSON output, as well as if you give, say, uh, input to the tagging model, the output again is like all the tags which are aligned by the model. And this is very useful because now you can actually just copy some of these into a publicly available visualization, which I showed you. Like you can either use the web-based UI, which comes as part of the library, or you can use this visualization, which will show you like just copy the JSON from the output in that Colab notebook and paste it here, and it will give you your visualization for whatever input text you had. And similarly, there is one for, yeah, there is one for classification. So this is the default, and you can also use it. So going, before I move forward, okay, I think I'll just finish this part also. So now, in the spirit of like aggregating data sets, I was also working on this problem of hateful and abusive speech identification for challenge at the end of my PhD. And like here again, you have this similar scenario that you have like multiple languages for which you want to perform this task. And you can think of it as multitask learning, but like here the tasks are different languages, but all of them share the same labeling schema. So you can use the same setup and get like pretty good performance on different types of like multilingual hateful and abusive speech tasks. And here, like I also introduce like some additional constraint which you can use as part of the task to improve the performance even further. And this one uses the BERT-based models as the embedding architecture. And it gives like really like a pretty good performance for all of these, and is available already as a publicly available model in the Hugging Face models models repository. So yeah, and like in a recently published paper, we also discussed like how different type of multitasking, for especially for classification, can be performed in a setting where you have multiple languages. So yeah, like it includes using like additional types of data, like say back translated data, or performing all the tasks together, or performing all the tasks separately. And we do a comparison of all these approaches. So next, I'll talk a bit about yeah. Before we move to this, like any questions on this part?
Yeah, so there were a couple of questions in the chat.
Yeah.
So what few shots methods are available to help reduce the need for large amounts of data? How appropriate is GPT-3 as a few shot learner for this purpose?
So I think so GPT-3. So the key idea which I have in this is GPT-3 again is can be used as a pre-training layer, and the few shot trainer which I have seen for GPT can be used to train this model. But the key idea is like how you train all these tasks together. So the current modeling architecture which I have is independent of like what this layer is. It's just that how you use the layers on the top. So like you can just replace this with the GPT model as your embedding layer, and then like you'll get similar performance. If you are referring to the few shot setting where you give the prompt to a GPT model and then you like let it like learn from just say a few different prompts, like the way you structure sentences, I haven't tested on that, but yeah, like that might also work. But you may have to come up with a good schema to represent these multiple tasks properly for this setting.
Okay, thank you. And another question is, what does CRF stand for?
Okay, yeah, sorry for not clarifying this. So CRF is a very popular approach for doing sequence tagging. So normally, like in the current, like people who are using BERT models these days for named entity recognition, the current BERT model, what it does is it does a softmax on each label, but that has its own label bias problem. That means like it will not be able to ensure consistency of the label. So sometimes you may have an I label before a B label, and that or like say an I label with no B label before, and that those are like inconsistent label. So oftentimes a CRF is a separate type of loss which is used. I won't call it a loss or a layer, but it's just a way like instead of scoring each individual token, each label individually, you score the whole sentence, and then you get the sentence space score, and then you back propagate your loss, like back propagate through the scores through the network based on that loss. So it's much more like accurate, and like it has a very good inductive bias that like even if like BERT performs well, like BERT with CRF like is going to like give you like a pretty good performance. Yeah.
Okay, and I have one question kind of from my side about the application. So I saw the tutorial that, like website that I guess you created for the International Conference of Computational Social Science.
Yeah.
And one of the applications listed is ranking users based on their enthusiasm and support towards social causes. So if you can, like in a few sentences, elaborate how do you rank something like enthusiasm of a user on social media?
Yeah, so actually that was another research which I don't think I'll have time to cover, but yeah, like the way we did is I did not have it in a presentation, but the way we do that is you have this sentiment task. So sentiment is like, again, I consider sentiment as a very ill-defined task because like what does it even mean to be positive? So we created a specific like taxonomy of labels. That means like you can either be enthusiastic about a cause or like supportive of a cause, and not enthusiastic and non-supportive. And then once you have those scores, you can run a variant of a PageRank algorithm based on the individual post scores of a user, and construct a network based on co-mentioned users, or like say users who have the same hashtag, who are talking about the same hashtag, and then use that PageRank score, which is weighted by their like these enthusiasm and support scores, to identify who are the most enthusiastic and supportive users on that topic. So it's an application where you need this scoring function, which comes from text, and then you construct this network, and then you run network algorithm to identify the top users.
Okay, thank you. And just as a heads up, I think we'll have about 15 minutes left.
Yep. 15 minutes left?
Yep.
Okay, thank you. Yeah. So the next thing I'm going to talk about is these are all like cases of training a model in a supervised fashion. Now, oftentimes, like again, we are operating in a very low data regime, so being able to efficiently generate labels is also a very important factor. And this is where like active learning or human in the loop learning comes into place. So what happens is that if you have a large number of, say, social media posts, and you don't have labels for any of them, like you can start with a smaller model and then use this active learning technique to identify that, okay, these are the new instances which should be labeled next. And then you can iteratively generate a larger corpus based on this. So I also tested this active learning approach, and it comes with a flavor of human in the loop learning, because active learning gives you some way of selecting examples, and then you have to perform like some labeling on those selected examples, and then you train the model and keep updating it. So the way it works is like, you take a model and some unlabeled data, and then you select samples from the unlabeled data to be annotated, and then you update your model based on the newly labeled examples. You can often, instead of just updating your model, instead of just adding your new labels, you can also often keep adding additional features to your model as you do active learning. And this is like one of the key difference of this human in the loop learning approach, which is different from the normal active learning where you just get like new items to predict on. Instead, you can keep adding new feature criteria, like so in case of sentiment, we can keep updating the sentiment lexicon so that, okay, we know that these words which we selected from this model are appearing to be, say, positive or negative, and then you can update them in your lexicon, and then you keep doing the incremental modeling of with this approach. And it gives pretty good performance. So if you hear, this is the dashed line, which is just training the whole model which is training a model on the whole data. And these are the lines which is like you do one round. One round is like around 100 samples. So you keep doing like for around 25 rounds, and you get like a pretty high score or very close scores on multiple of these data sets as your model like improves. So this is a pretty good way to see like how to quickly collect labels and then like get a similar performing classifier with like less labeled data if your label examples are chosen correctly. And also like, yeah, this gives, so here I also evaluate like based on the currently non-touched examples, like what is the model performance, and like the model performance is increasing, which says that, okay, like whatever is remaining, the model is actually continuing to improve on those remaining examples much faster. So I will close this section now. Like here is a link of some of the resources which I have presented till now. Now I'll quickly, like before I finish, I'll talk about the idea of digital social trace data. So initially I mentioned like social media dataset has some sort of context. So what do I mean by that context? So earlier, like when I mentioned like information extraction, you can think of information extraction as just taking some unstructured data and convert it into some structured format. So structured format can be some database, some graph, or something else. And oftentimes what happens is your data set is not actually fully unstructured. It actually is semi-structured. So you have like some metadata attached to each post, so each text, and you can use it to like get like better information extraction system or even better analysis. So the way I have defined like a digital social trace data is like data sets which are generated from social interactions. And they are often available like in settings like, say, social media platforms, but also in some non-social media settings like scientific publication. I'll give an example how. So here is how I define, like give an example of two different types of digital social trace data. One is social media data. It has a temporal component. And then like you have, say, tweets which are not existing independently, but they exist in context of some other tweets. They exist in context of the users and the users' metadata. Some of the metadata is already available. Some of the metadata needs to be inferred. And then these often like are related to some other larger context, like say tweets which share a hashtag, tweets which share a URL. So these are like external contexts, and you really need to utilize all these information to actually make sense of what that data is talking about. Now this problem like is like much broad, but like you have like a much more refined setting here in scholarly publishing, which is that you have like papers which are related to other papers, the way they cite, and then you have papers related to authors, and then these authors are also connected to each other. So you get like this shared context. So if I know like this author published on, say, deep learning, like the other paper is likely to be on deep learning, and you can use this context to perform tasks, say like, topic classification of papers and do other things. So what are the properties of digital social trace data? Like first, it has to have temporal information. Next, it needs to have presence of connection between various data items. And lastly, like it needs to optionally have like some associated metadata, like say like retweets, other things. So how we can use it? So I will give you an example of how we can use it to improve, say, tweet classification. And oftentimes, like the way we perform, like say sentiment classification, we just like look at the tweet text, and then we try to infer like, okay, what is the sentiment? But what we discard is like all these additional metadata which is already available. And the key idea is like, can we use this additional metadata as features to the model and see like whether it causes an improvement? So each metadata actually has some significance. So, and like, again, this is the significance I classified under different levels. So like some reflect activity level, like people who are more active, people who are more social, like, so they have a lot of friends or they have a lot of social status in terms of number of followers, authenticity of their profile. But they also have like other tweet level characteristics, like this tweet is a reply or is it a quote? How many URLs does it include, or how many hashtags and all those things. And what we found is that like often these additional attributes are actually highly correlated with the sentiment labels. And as you see, like, the correlation is not necessarily fully linear, but like it has a strong pattern across all the different labels for each of the sentiment. And some of the things like, say, number of mentions, number of hashtags, these don't necessarily have additional labels. But things like, people who have a lot of friends or people who are a lot of followers, these things are highly correlated. Again, it is very important to note that when I say these are correlated, it doesn't mean that like, if I have a lot of followers, then that means like my tweets are not going to be negative. Like you can still have that. It's just that if you include this in the model, you can like smooth things out and get pretty good patterns. And what it found is that like, normally if you just train a model with just the text data, you will get like around say 72% performance. But by including this joint data modeling, you often get like around close to 2%, 2 to 3% improvement across all these different data sets for the sentiment task. And the way I look at it is that it's somehow like these simple attributes are capturing some aspect of a user embedding or a tweet embedding which exists in the network. And these are helping the model improve its performance. Next, you can use, because now we have this digital social trace data framework, you can use it to also like visualize these data sets. So I built a visualization framework called Social Communication Temporal Graph, and I will show you an example of that. As there's like, so oftentimes like you have a Facebook group. These Facebook group communications don't exist necessarily on their own. They are like exist in temporal context as well as some social context. So here, like on the top, these are all different posts. The bottom, these are the various comments to each of the posts. And you have comments colored by like, different types of users. And you can use this to visualize also like say things like tweet sentiment. So you can know that, okay, this user has tweeted like say 3 times, and most of the tweets have been like positive, and like one tweet has been negative. And you can know that, okay, which are say the most popular users, what is their sentiment, which are the say less popular users, what is the sentiment they're mostly talking about. Again, this is a freely available tool, so you can go and check it on the website, which I've listed here. I think I have one example open here. Oh yeah, so this is another example of like say users who are like say tweeting about a given entity, and here I'm comparing a collection of users who are talking about 2 different search terms and how do they tweet. So this is a user who has talked about both the search terms, like 2 politicians, and what is the sentiment of their tweet for each one of them. So you can use it to also compare like say users which are posting about different topics. So now to close, I will also give some inspiration, like, how this is linked from scholarly data. So in my PhD, I've also worked a lot on scholarly data. And in scholarly data, the world is slightly nicer because you have a lot of attributes already available. And one of the things which I presented earlier is like finding information from text, from social media data. Those things are already taken care of in scholarly data world, where you already have like say papers which are assigned nice topics, especially like in biomedicine, where each paper is hand annotated with say like some of the core topics in biomedicine. And you can use this to to do like some very interesting inferences. So for example, if you just consider paper as a set of concepts, you can actually do something like see how a concept evolves over time and see how its growth can be modeled over the years and which paper are often published in which stage. So for example, here we came with this idea that often each topic has this burn-in phase where like few people are publishing on that topic. Then you have this accelerated growth phase where everyone starts publishing on this topic, and then this growth decelerates, and then it becomes constant. So okay, there's a constant number of paper improvements every year for this topic. And now once you have this idea of a temporal profile of a concept, you can use it to assign novelty to a paper. So what is the most novel topic on a given paper, and can we use it like, okay, which are the papers which are most novel? And also you can use it to assign expertise to individual authors. So like remember, like we are living in a digital social trace data framework. So we have for each paper, we have authors assigned, and we can use it to track how the expertise of people has changed over time. And yeah, that is it. Most of my resources are available on my PhD thesis page. And yeah, I'm available on Twitter if you have any questions. Thank you.
Thank you so much for your presentation. It was very interesting. I think we have one question in the audience, and I have a couple of questions too. So you were talking about this as a research, and I was wondering what kinds of practical applications are already in place or planned to be perhaps on Twitter, or well, since you work on Twitter, that probably would be the right place for you applying this research into. So could you tell us a little bit more about the practical applications and how it's used?
So in terms of practical application, most of my research, I've already applied it to basically scholarly data sets in terms of the digital social trace data framework. And we used it to identify expertise of authors and like a novelty of papers, and come up with like inferences on how science evolves over time. But when it comes to like some of the more machine learning aspects which I presented earlier, those are like very generic and can be applied in social science. So again, there's a large field where people just work on identifying patterns on, say, social media platforms, say like, okay, how hate speech is spreading. Or like there was, I think, like a very interesting study like a long time back. It said like anger spreads faster on social media than, say, other emotions. So there they need these models which assign these labels to each tweet. And oftentimes what people do to come up with those inferences, they just say either take a dictionary based approach or take some off the shelf model without knowing that these things are not designed for social media data. So that is the key area I'm aiming at, and people are trying to use it for some of those aspects. So like the Twitter NER, which is like the oldest project, it has already been used for a lot of analysis for identifying named entities. The social media IE is a very new tool. I made it at the end of my PhD, and it's only, I think, like last year I open sourced it. So yeah.
Mm-hmm. That's very interesting. The question from the audience is, how do you represent all these different data types? For example, friendship graphs and social media. How do you get from a graph to NLP model in particular?
Yeah, actually, so that's a very interesting challenge. So in my case, I have used two different instances. So for scholarly publishing data, I used to represent each paper as a collection of concepts and then as a time variable. And then I was generating this time series for each concept. So it required doing a lot of say, PySpark jobs, which ran I remember running it for. So I was working with 22 million papers and around 22,000 concepts. So it required around spread across, I think, more than 50 years. So it allowed like running all these things and representing. So, but even just the start point is having this representation at an individual level, which has these additional metadata like time and concepts. And then you can just run any aggregation. So either in a graph fashion, which I did for the sentiment page rank thing, where I just took like labels for each tweet, and then I constructed the graph by aggregating. So oftentimes it requires like some additional aggregation. Yeah.
Mm-hmm. Alex, do you have questions?
No, I think we're good. Thank you, Shubhanshu.
Thank you.
I'm gonna add our other presenters back to the stream. Hello again. Thank you everyone so much. You've made it a great meetup. I don't think we ever had 3 speakers at the same meetup. We usually have 2, but I think it made it only better. And I personally enjoyed all of the talks, and I'm looking forward to meeting you in person at some point in the future. Hopefully, I hope folks in the audience enjoyed the meetup as well and enjoyed the talks. And we've shared the links. So the links to the slides, the links to the GitHub projects and notebooks. So folks have stuff to look at and to continue learning. I'm definitely going to be playing with the notebooks. It's always fun to get your hands on something new. And yeah, thank you all so much. Alex, would you like to add anything?
No, just thanks everyone for making time for us. I know it's after a full workday. It might have been a long day for everyone, so please enjoy the rest of your day.
Yes.
Thank you.
Thank you so much.
Thank you.
Bye.
Thanks for having us.
Bye.
Bye.
Bye. Bye.